Good morning. This is the elevator pitch for the paper, Distributed Training on a Highly Heterogeneous HPC System. And this is involved in this publication is involved in the Deep Health project. So let me go next slide. So this is the context of our project, the Deep Health project. So it's an H2020 project from ICT 11 and is running from, we are in the second year, so started in 2019, we'll finish end of next year. And the project targets HPC and big data enabled large-scale testbeds and applications. So we have 21 partners, so you can list there, you can see there the logos of each partner. So the goals of the project are different. So here you can list the major goals. So this is the first one is to achieve distributed training of neural networks for medical applications. And in order to achieve this, the project is developing an open source European library for training and inference. So we call it the EDDL. This is the European Distributed Deep Learning, and the ECVL, that this is the European Computer Vision Library, that both will be complemented. So the second goal of the project is to use these libraries and to adapt it to heterogeneous systems for CPUs, GPUs, and FPGAs. And what we mostly target in this project from the computer architecture perspective is to match the artificial intelligence algorithms and the HPC systems. So here you can see the different use cases that targets the project. So you can see there are many of them that will be using the libraries and then will be mapped on HPC systems. So the type of systems that we others are very heterogeneous by nature. So here you can see that we spawn from CPU-based systems like the Mare Nostrum supercomputer in Barcelona Supercomputing Center. And we can reach even the experimental Mango prototype that is full of FPGAs, and the algorithms and the library should be running on these devices also. So this is a very challenging project from the perspective of the hardware. In order to do that, we need to identify the problem that we face. Here you can see in the picture that we have below the hardware that can be very heterogeneous. So for instance, you can have different nodes in the same system only with CPUs, with these ones, or you can have only GPUs, with this one, or even you can have FPGAs, nodes with FPGAs, or even a mixture of the devices. So this is the hardware that we should face. On top, you can see the algorithm, the problem that we are trying to map on that hardware. And basically is the distributed training. So what we are targeting is the data parallelism for training neural networks. This means that the input set is distributed and the different nodes should compute different batches, and then they should communicate and synchronize the different parameters of the neural network during the training process. So here you can see that we will have input data. We will have also shared data that will be synchronized. And we have also what we call kernels, and this is the basic operations that we perform on the data. So the target that we focus in this presentation and in the project is how we effectively map all this process into the different hardware that we already have. So we follow two approaches. The first approach, let's say that this is an internode approach, is the distribution of the different batches onto the different nodes. For that, we will follow an approach that is a test-based programming model that is implemented through the COMS programming framework of Barcelona Supercomputing Center. And in that approach, we split the batches, the training batches, into the different devices that rely on different, reside on different nodes. Okay. So basically, COMPS is a framework to develop parallel applications for distributed infrastructures. It presents an abstract model where we expose the parallelism while we are hiding the infrastructure details. So it is supposedly is agnostic of computing platform. Okay. So this is for the first, the top level approach. But then at the node level, we should also care about how we distribute the computation and the data. Okay, so we can go easily from a GPU-only mapping in the sense on the left that both the kernels and the data are located on the GPU, and then the CPU is only used to command the training of these batches. But we could do also the same in the project just for FPGAs, where we have the kernels on FPGAs and also the data, the tensors, are located on the DDR memories of the FPGA devices. But what we aim also in the project is that we want to have an heterogeneous usage of devices in the node, where we can have FPGAs, GPUs, and even to use the CPUs for some parts of the training or the inference process. Okay, so basically here we can see a hint about how we are developing this support. Basically here you can see on the right the part of the flow of a training process of a batch. Basically maybe you can have the convolutional process that is doing the convolutions, and then you perform an activation function, and then you multiply by the weights of one layer. And here we can see an example where you decide that the convolutional is mapped on the FPGA, and the rest of the process is mapped on the CPU. This could be for different reasons, maybe for power consumption, for efficiency, or for precision, or for whatever reason that we should consider in the project. So having this in mind, so the way that we approach this intranode heterogeneous support is basically towards what we call the CPU emulation, for instance. And here you can see a piece of code where the activation function, the rel activation function, is implemented with support for both devices, for the FPGA, or in this case, for CPU support, but being compatible with the tensors that are located also on the DDR memories of the FPGA. For that, we are managing direct access to the devices from the CPU or from the GPU, from the different devices, that they should perform as efficient as possible, okay, in order to allow that the ReLU activation function finally is computed on the CPU, okay. So this is the approach that we are following. And then just to conclude this elevator pitch, here you can see the current status that we have functional implementation of both the internode heterogeneous support, and in process during the project we are implementing efficient intranode memory access. So this will be based on MPI and remote direct memory access and GPU direct, and what we call FPGA direct support, and efficient internode memory access that is in progress because we are working towards having direct device access from other devices. So to conclude, preliminary results will be provided in the paper and on the presentation that we hope to see all of you next year in SAMOS. So this concludes the presentation. Thank you very much.